Good morning. My name is Aditya Venugopal Nedrugal, and this is my presentation on hybrid modeling on radio frequency link and free space optical signal attenuation. In this talk, I'll walk you through the motivation, methods, implementation, and evaluation of a data-driven approach to predict signal attenuation in hybrid optical radio frequency communication systems under different environmental conditions. Modern communication system faces signal degradation due to atmospheric disturbance like fog, rain, and turbulence. Free-space optical links are especially vulnerable, and while radio-frequency link signals are more robust, they have lower bandwidth. Combining both forms a hybrid system, which demands accurate modeling of attention under dynamic weather conditions. Traditional physics-based models often fall short in handling non-linear patterns and multivariate conditions. This is where machine learning comes in. Our objective was to develop models that accurately predict free space optical and radio frequency attenuation levels using environmental parameters as input. The challenge lies in dealing with real-world weather data, which is noisy, skewed, and highly imbalanced across conditions. We aim to build interpretable, generalizable models that support real-time decision-making in telecom, aerospace, and defense communication networks. We had three goals. First was to evaluate the performance of general models using versus the random-specific models. Second, to explore the impact of feature selection and hyperparameter tuning. And finally, to test if a hybrid two-step model using radio frequency attenuation can improve FSO predictions. This work has practical applications in developing resilient hybrid radio frequency systems and FSO systems. Our dataset contains 27 variables, including temperature, dew point, visibility, pressure, wind speed, and various cloud and turbulence indicators. The main two target variables are phase space, optical attenuation, and radio frequency attenuation, known as FSO underscore ADT and RFL underscore ADT. Additionally, the sign-up code is a category identifier for local weather stations and used for location-specific modeling. In our dataset, we can see that the sign-up code help us to segment dataset based on regional weather patterns. By training per sign-up models, we allow the model to learn from region-specific environmental interactions. Later in this project, we will also evaluate how effective this approach is compared to global model. Removal of outliers. Before we even start our field selection, we can see there are some existence of outliers in our data set, and in order to deal with this, we decided to remove some of the outliers, as we can't remove all the outliers because these are remaining outliers could be some distinct cases. Correcting the skewness. As we can see from the above information related to skewness, we can see that few variables related to particles and rain and wind have a lot of skewness in them. This skewness variables were transformed and normalized, especially using for long-tail features like visibility and solar radiation. Skewness metrics improved dramatically, making features more usable. The features were skewness was improved and removed by using two methods, that is square root transformation and applying the power transformation. Since applying these two transformations, we can see the difference in the skewness has reduced, and hence we can use them. Now coming towards data splitting. So we perform data splitting for a model building to build accurate predictive models. We split our dataset into training and testing sets. This ensures that a model learns from one part of the data and is evaluated on data for fair performance measurement. The train test split. We divide our data set into 80% training and 20% testing to develop and evaluate our models. So why does splitting matter? Well, it prevents overfitting, it ensures fair evaluation of the model performance, and it helps to check if our dataset is balanced across different weather conditions. Now, the training set is used to fit the model, while the testing set is used to check the model accuracy. In the next slide, we will discuss how the general models versus per sign-up models were built. Now, building general models for radio frequency and FSO. So we remove the target variables and use all the environmental features. The data was split into 80% of training and 20% of testing and evaluate the model performance. We use random forest regresses with 100 estimators and enabled the auto score. We can see the following metrics. We can see that for better a better model means it has lower RMC score. The R square must be very much close to 1, and the automatic score tells how the model is able to generalize. When we compare the models, we can see that the FSO model is high RMSE, means it struggles to predict very accurately, while the RF model or the radio frequency model has lower RMSE, making it more precise. The R square, well, in both the cases, is way too high, which means the model explains most of the variance, which is good. And the overall conclusion will be the radio frequency model performs slightly better than the free space optical model, and the free space optical prediction have more uncertainty is due to weather impact. Now, downsampling the set. We know that how important it is to downsample a dataset if the dataset is too big or is imbalanced. In our case, it's both. So, as you can see in the before pictures, the dataset is very imbalanced based on per sign of code. So we use the algorithm and we downsample the dataset, which makes it a bit balanced. And then in this balanced dataset is where we make our next models. Now, feature selection. Now, feature selection is a very important part in making our models. So what we do, we use a algorithm called as backward feature elimination. In this step, the least important feature based on the feature importance was removed, and the final selection features were saved. And based on these final features, we make models. So as we got the final features, we developed two models. That is the optimized RFL radio frequency models and optimized free space optical general models. So the optimized radio frequency general model had a lower RMSE, which means it has better accurate predictions, and it had more higher I square. That means it had more correlation between the input and the output, and the OAP score tells it generalized very well. And in the case of optimized general FSO model, it had a bit higher RMSE, which means the signal variation was high, and it had a better R square, which means it captures the patterns very well, and the OAP score tells that the overall performance of the model was very well. Now, comparing the generalized RFL model and the generalized FSO model. So we can see that the optimized RFL model perform a bit better than the optimized FSO model with the lower RMSE and higher R square. The FSO model had higher RMSE, which means more variation in the predictions. Both models had strong OAB scores, meaning they generalize very well. Conclusion: the optimized general RFL models or the radio frequency model give more stable prediction, but the generalized optimized FSO still captures key variance. Now, as I said, now it's time to create per sign up model, which means we'll create 7 different models based on 7 different sign up codes, and we'll use the same features that are final features and create 7 different models, 7 different random forest models. And the key findings of doing this, we can find that some sign up models had very low RMSE, which means they had better accuracy, and the R squares of for almost some of the models had were high or maybe close to 1, which means they had excellent predictions, and the scores confirm these models generalize very well, as we can see in the figures. Now, comparing the general models and the per signer models. So, why should we now compare the optimized general models and the per signer models? Well, we are doing this so that we can understand how these models operate and what's the RMC and which models is better in prediction. So, these are the conclusions. The per sign of radio frequency models have lower RMSE and had more accurate predictions, while the per sign of models show better out of back score, which means they generalize better than the general models, while the FSO models generally have higher RMSE than RF models, indicating more sensitivity to weather conditions. So now that we got the models, now it's time to hyperparameter tune them so that we can get even better predictions. So why should we do hyperparameter tuning? So it helps us to find the best setting for the random forest models. It improves the accuracy, as I said mentioned before. So we use the following parameters, and then we got the the RMSE score to be improved to 1.038, which means it had better accuracy. The R square was 0.9613, that means it has strong predictive power. And the out of bag score is 0.9608, which means the model generalized very well. We did the same for the RF model, and we can see that the RMSE score also improved. The R square for the radio frequency model has also gone close to 1, and the auto bike score has gained a strong generalization, which means that hyperparameter tuning was very successful for both of the models. Now, time to compare the hyperparameter models and to see that which model is better. So when we compare the optimized radio frequency model and the FSO models, we have the following conclusions. The radio frequency model has lower RMSE, which means it has better predictive accuracy, while the free space optical model has slightly better R square, showing strong correlation between the target variable, and the both models perform very well after hyperparameter tuning, showing balance improvement. Now, we now it's time for another method. In this method, we will develop a radio frequency, another random forest model. This model will be trained to predict the radio frequency attenuation, and when we do that we see the RMSE to be 0.770, the R square to be 0.9381, and the out of whack score to be 0.9317. And when you look at the scatter plot, we can see that the model was the, the points are very much close to the red line, which means it has better accuracy. Now that we have we have already predicted the radio frequency attenuation. Now we will treat it as a feature to predict the FSO model. And when we do that, we realize that the RMSE has increased, the R square have decreased, and the OAB score has also decreased, which makes us to come to the conclusion that this theory or this process was a complete failure, since we were expecting it to be shows a better performance, but however it shows no improvement, which means that RFL has RFL prediction has very much less influence on FSO attention. And when we do the correlation, we can see that this correlation score is in negative, and the mutual information score is very less, which suggests that no linear dependence and almost no linear relationship. Hence, the first theory that RFL attention has something to do with FSO attention seems to be a failure. And hence, we go to the next step, that is making the seven models for seven sign-up codes, and without including the RFL attenuation, and we can see the performance. We can see that the performance is now increasing, and the difference is very much evident, as we can see that the trained random forest model for each sign-up code using backward elimination as compared to the general models, we can see these are the following comparison, and we can see that the sign-up code has performed very much better than the general models. And these are the feature selections. We can see that uh, the humanity features were one of the most important features, and one of the most contributing features for the sign-up codes. Now it's time to compare the first method and second method. As we can see that first and second method, we can see that the first method had lower RMSE, showing more prediction. However, the second method shows more variance and more OAB score, and had even though it had a high RMSE, but it's very simple to implement. And we can see the following feature interpretability and selection for the FS attention, and the feature interpretability for the FS attention as well. My conclusion will be that the first method uh, was the best model, but first and code is better because it has lower RMSE. The score is better. So if you prefer simplicity, we will go for hybrid model, that is method 2. But if you want accuracy, we should go for method 1, that is per signed up models. In future, we would like to include LSTM models and neural networks